Welcome to solverfy.
In question 18, we're asked which type of intermolecular force accounts for each of these differences. So in part A, they're telling me that CH3OH, its boiling point is equal to 65 degrees Celsius, where CH3SH has a boiling point equal to 6 degrees Celsius. So why would that be? So what you want to look at is the difference in intermolecular forces, figure out what type of intermolecular force each one of these has. Well, they both have LDFs, so and there's not a significant difference there. That's not going to account for our issue, so we don't really need to worry about that. The difference here is going to be that the CH3OH molecule can have hydrogen bonding. Because hydrogen bonding is between a molecule with a hydrogen that's bonded to an F, O, or N, and then that F, O, or N. So I have hydrogen bonded to an O here. So this molecule can hydrogen bond. CH3SH cannot hydrogen bond. Sulfur is not F, O, or N. It is a polar molecule, so it will have dipole-dipole interactions, intermolecular forces. However, regular dipole-dipole forces are in general not as strong as hydrogen bonding. Therefore, hydrogen bonding is the stronger intermolecular force, and it is therefore going to have the higher boiling point. In part B, we are looking at the difference between xenon, which is a liquid under the conditions given, where argon is a gas under the same conditions. So if this is a liquid, that means it must have stronger intermolecular forces. The intermolecular forces here must be stronger, thus holding it together as a liquid. So what kind of intermolecular forces do these have? Well, they're single atom nonmetals. So the only type of intermolecular force either of them can have is LDFs. So they both have the same type of intermolecular force. So then we have to break down why the LDF of xenon is stronger than the LDFs of argon. And when you're looking at LDFs, London dispersion forces, you generally want to look at molar masses. Xenon has a greater molar mass, and because of that, that means it has a larger electron cloud, and therefore the larger electron cloud is going to make it more polarizable. When it's more polarizable, that means when the electron cloud is polarized, that's what happens in an LDF. LDF is interactions between polarized electron clouds. So because xenon has the larger molar mass, the larger electron cloud, and is more polarizable, it is going to have the stronger London dispersion forces and therefore be a liquid under those conditions. In part C, I'm looking at the difference between krypton, which has a molecular weight of 84 AMU, and its boiling point is 120.9 Kelvin, where chlorine, Cl2 molecule, its molecular weight is only 71 AMU, but its boiling point is up at 238 Kelvin. So this is a nonmetal atom. So the only thing again that it can do is LDFs. This is a nonpolar molecule, and so all it can do as well is LDFs. So again, we're looking at the difference in LDFs. Now, generally, we would go with the one with the higher molecular weight being the stronger, but we can see that in that case it has the lower boiling point instead of a higher melting point. So the other thing that's involved here is the shape and the amount of connection that the molecules can have with each other. Krypton is just a single atom, so it can kind of interact. Its electron cloud can shift, but it's a spherical atom to begin with, and there's not a lot of connection points between it and another spherical krypton atom. Here we have Cl2, and because it's two atoms bonded, we can think of the electron cloud as more oblong. And so here you have kind of a greater surface area in order for one Cl2 to form an intermolecular force with another Cl2. There's more kind of connection here. So the clouds, the electron clouds are more polarizable. We can have this greater interaction between these, and therefore this is going to have a higher boiling point. In part D, I'm looking at acetone. And acetone is going to look like this, C, and then I have a double bonded O, CH3 bonded to CH3 versus 2-methylpropane. 2-methylpropane looks like this. I've got a methyl group coming off of here, and there's my propane with 3 carbons. And they're telling me that acetone boils, it's this boiling point is equal to 56 degrees Celsius, where this boiling point is equal to negative 12 degrees Celsius. So this one has the higher boiling point, and in addition, it has the stronger intermolecular forces. So what types of intermolecular forces are we looking at here? Well, let's go over here. These guys are primarily carbons and hydrogens, and they carbon and hydrogen have similar electronegativities, and since they have similar electronegativities, they are primarily nonpolar bonds. The difference in electronegativity falls in the nonpolar covalent range. Therefore, this is a nonpolar molecule, and so the only type of intermolecular force it can have is an LDF. This guy right here, our acetone, with this oxygen group on there, this is going to make this molecule polar. And because it is polar, it can have dipole-dipole interactions. It will also have LDFs, but the addition of the dipole-dipole is what makes it have stronger London dispersion force, stronger intermolecular forces, and therefore the higher boiling point.